Session is President Campbell, who'll tell us about geometric glass field theory and Cartier duality.
Okay, thanks very much to the organizers for inviting me. So yeah, this is my first time giving an online talk like many of the other speakers. Also, 25 minutes, this will be interesting. So I have something like 1 slide per minute. So probably I'll pick and choose what I actually say. Just a quick comment on this work. So it's joint work with Andreas Hayash, stuff that I've been thinking about on and off for, I don't know, maybe 6 or 7 years since I was a grad student. And so it's of questionable originality. A lot of this project is kind of collecting some folklore, maybe systematizing certain things that are not well documented. So I'll try to be explicit about what is actually original and what's not. And I'm also happy to be correct that someone brought to my attention just a couple of days ago some papers that have some overlap with this work. So I'd be happy to find out also about anything in the literature that I was not aware of on this topic. Yeah, and relatedly, it'll be probably more elementary than a lot of the other talks. So it might bore the experts, but everybody else can kind of sit back and relax. Okay, so I'll work throughout over an arbitrary field, and I have a smooth geometrically connected curve, not necessarily projective. Everything will be over K. And I fix a smooth projective closure of my curve, which maybe affine. This X bar, I mean, it is more or less canonically attached to X, but it sort of plays an incidental role. So I'll comment more on that in a minute. I will be the set of closed points in X bar not contained in X. And this is kind of a revisionist usage of this terminology, but for me, the Jacobian of this curve X, it's the commutative group stack, which I'll denote by pick of X comma boundary of X. So it parameterizes line bundles on the projective curve X bar equipped with the trivialization over the formal completion of each point, each closed point in the complement. So yeah, in fact, I said commutative group stack, but as long as X is not projective, this will actually be a scheme, commutative group scheme. It's only a stack in a non-trivial way if X is actually projective. So it's, I call it the Jacobian, it sort of contains sort of what you would think of as the classical Jacobian, this abelian variety as a subquotient, but it's slightly more complicated. So typically, again, if X is not projective, it's of infinite type. It contains, subgroups that look like arcs into GM. And in case this notation looks weird, I could also say this in a slightly more complicated but maybe more satisfactory way as parameterizing line bundles on X equipped with a trivialization on the punctured neighborhood of formal neighborhood of each point in I. So you can define it without referring to X bar, but as I'll comment on later, working with these punctured neighborhoods is a little bit technically annoying at times. So this is just an easier way to define it. Okay, and this Jacobian, it receives the AutoJacobian map, very standard construction. So I can attach to any point on my curve X the corresponding line bundle. It's a line bundle on X bar really. And it comes with a canonical section, right? So we have this canonical map from the structure sheaf to this O of the point X. And this defines a point of the Jacobian because, well, since this canonical section, it doesn't vanish away from the point X, right? So in particular, it determines trivializations of this line bundle over the formal completion of each point in I. So indeed, it determines a point of the Jacobian. So this is kind of the, like I said, standard construction of the AutoJacobian map for a affine curve. And the basic kind of statement that we're interested in is what I would call an Albanese property. Again, these words like Albanese, Jacobian, AutoJacobi all get used in like slightly different or maybe interchangeable ways. But for me, the Albanese property, it says something like, for some class of groups, G restriction along the AutoJacobian map induces an isomorphism from homomorphisms from the Jacobian into G to the collection of maps from the curve into G. So this is known for many different G, right? And so for different kinds of G, maybe there are different arguments. And part of my ambition with this project was to kind of systematize this and provide some unifying framework for this sort of Albanese property. Right. So by way of motivation, let me explain what this has to do with geometric class field theory. You could view this Albanese property as some kind of very generalized geometric class field theory, but let me say how to recover the more familiar classical statements. So I can take my target stack to be the classifying stack of a finite abelian group in the topology, say. So maps from X into this classifying stack will consist of étal A local systems, meaning A torsors, which are étal locally trivial. And of course, that can be identified with continuous homomorphisms from the étal fundamental group of X into A. Or, of course, I can replace the étal fundamental group with the abelianization. On the other hand, so what appears on the other side is homomorphisms from this Jacobian into this classifying stack B of A. So these are exactly multiplicative A local systems on the Jacobian. So a multiplicative structure, again, it's a fairly standard concept. I think sometimes people call these, character sheaves. There's a few different names, but it's just the following structure. So I give myself a trivialization of the fiber at the identity, and I give myself an isomorphism of the pullback of the A local system along the multiplication map with the box product of it with itself. Of course, there are some natural associativity and unitality conditions that I won't comment on, but this is just what you get if you unwind what it means to give a homomorphism of commutative group stacks from the card to B of A. Okay, so in this formulation, this identification of A local systems on X with multiplicative A local systems on the Jacobian, this is sort of, I think people usually attribute it to Deligne's formulation of geometric class field theory. And as is pretty well known, it implies the function theoretic or more classical art and reciprocity isomorphism. So let me quickly explain that. So suppose the ground field is finite, and I'll write, just for notational brevity here, J for the Jacobian. So the trace of Frobenius construction, it allows us to assign to any multiplicative A local system on J a homomorphism from the group of FQ points of J to A. And I have to write continuous here because, again, this J, it may be, well, typically, if X is not projective, it's of infinite type. So it has something that looks like, units in the local ring in there. So you should really say continuous. And this map, in fact, for this particular group J, it's an isomorphism. So this is a consequence of essentially of Lang's theorem. So if I allow A to vary here, then I formally obtain an isomorphism of profinite abelian groups between the profinite completion of the FQ points of J and the abelianization of the étal fundamental group of X. And this J of FQ, it's exactly the quotient of the Adele class group that appears in art and reciprocity. And I claim this isomorphism is exactly the art and reciprocity map. So this is how from this kind of Albanese property, we can extract global class field theory for function fields. So in particular, notice that I allow arbitrary ramification at some specified set of points. Okay. All right, so let me move towards kind of the statement of this generalized Albanese property that I want to make. So standard notation for any pre-stacks. So by that, I just mean, anything with a functor of points valued in groupoids, I can attach to it a mapping space. It's standard notation, right? So it's, again, a pre-stack. Likewise, if I have two commutative group stacks, G and H, then I can consider their internal Hom, defined by this formula. Okay. So what I'll call the Cartier one dual of a commutative group stack, it's defined as the internal Hom from G into classifying stack of GM. So I call it the Cartier 1 dual because usually when people say Cartier dual, they mean, I guess, what with this convention would be called the Cartier 0 dual, right? So that would be internal Hom into the multiplicative group itself. So for me, the Cartier 1 dual is Hom into BGM. It's the kind of duality you would consider if you were talking about duality of abelian varieties, for example. Right, so that's, it plays a distinguished role, in, at least in this setup, this one duality. And I'll say that a commutative group stack is one reflexive if the natural homomorphism to its double dual is an isomorphism. Okay. So you might sort of naively guess that you could formulate some parameterized version of the Albanese property. And it's not just out of idle curiosity that I would want to do some parameterized version. I think it's sort of necessary. Maybe I'll comment on this in a second, for many applications in order to really do this in families. It's not just because I'm a fan of Grothendieck and I want to do everything in families. It's really necessary for some things. So I'll comment on that in a second. But I'd really like to formulate the Albanese property as an isomorphism of commutative group stacks, something like an isomorphism between internal Hom from the Jacobian into G to the mapping space from X into G. So an isomorphism of commutative group stacks. And you might hope that this is true for any one reflexive G. That's a very nice class of commutative group stacks. So in fact, in this formulation, this is true for X proper. And I proved this result in a preprint from a few years ago, which this project is kind of an update to. So you can find that on the archive on my website in the proper case. But in fact, this formulation fails for X affine. So the basic issue is that, well, here, let me give a counterexample so you can see the issue. So take X to be the affine line. So there are some counterexamples due originally to Bass. So from this paper from 1962, he exhibited a bunch of examples where there are line bundles on A1 times some test affine scheme S, which are not pulled back from S. So it's kind of just this by now well-known phenomenon that the Picard group is not kind of, what's the word? It's not A1, it's not invariant under multiplying by A1, right? It fails this type of homotopy invariance, or whatever you would call it, fails. A1 homotopy invariance. So this doesn't match up with what's going on the other side. So in fact, any S family of multiplicative line bundles on the Jacobian, with X being the affine line here, is pulled back from S, at least locally on the base. So it's pulled back from S. So the two sides don't match up in this case, and the space of maps is larger. It's a phenomenon that I personally would like to understand better, but I can sort of understand Bass's example, but I don't have any handle on how to really classify or anything to say about the Picard stack of A1 in general. It seems quite wild. So we need to somehow cut this down to something manageable. And this is where, as far as I know, this is kind of an original definition, but we do it in kind of the most naive universal way. So if I have a map from X times my test scheme S into G, so it's a family of maps from X into G, I'll call it BGM extendable if for any homomorphism from G to BGM over S, an S family of homomorphisms, the composition, so I obtain from this a line bundle on X times S, and I require that extends to the projective closure, at least locally on S. So certainly I think in the case when G equals BGM, this is a definition that people have made before or known to consider. So when you run into this issue that line bundles, the moduli of line bundles on an open curve is kind of wild, people know, well, you should really only consider line bundles that, families of line bundles that kind of extend to the projective closure, and this will make things more manageable. So all I'm doing here is I'm kind of making this in some universal way, I'm making this definition an arbitrary G, but I don't do the naive thing and require that the homomorphism into G extends. I only require that the induced line bundle extends for any family of homomorphisms from G into BGM. Right. So, and let me write maps superscript X for extendable for the substack consisting of BGM extendable maps. So again, it's a funny condition. So notice that this condition, so any line bundle on X, like not a family of line bundles, but just a line bundle when the test scheme is actually a point, extends to the projective closure, of course. So this inclusion is an isomorphism on K points. It's only a non-trivial condition on families. Again, I didn't know what to do in this situation for a long time because you see right away that it's not correct to require that the map from X into G extends. It's not the right condition. So for example, if G is classifying stack of a finite abelian group, of course you don't want to require that your local systems extend from the affine curve to the projective curve, then that would be saying that they're unramified. It's not very interesting, right? So instead we put this BGM extendability condition. And so we formulate our theorem thus. A restriction along the Jacobi map induces an isomorphism of commutative group stacks from the internal hum from the Jacobian into G to this modified mapping space of BGM extendable maps from X into G. And this holds for any one reflexive G. Okay, I see there's some questions in the chat. I don't know if the correct thing to do is to try to answer them now or wait. Okay, looks like Andreas about that.
Taken care of, so.
Okay, great, thank you. Yeah, the case of two duality and higher is certainly interesting if you're interested in things like Brouwer groups, right? So it's something that I'd like to think about more. Okay, so now let me say some words about the proof, or first, let me say what happens if I specialize to the case G equals BGM itself. So in that case, there's this result, which it's Cartier duality results, and it says that the one Cartier dual of the Jacobian is exactly this moduli of extendable line bundles on the Picard. So here, since the target is BGM itself, this extendability condition really means line bundles, families of line bundles, which extend to the projective curve. I actually, this is certainly something that experts know. It's not something that I know where it's documented in literature, and I can be happy if people could point me to something, but as far as I know, it's folklore, but I could be wrong. So that's a special case of this result, but in some sense, it's the most important special case, and our proof essentially proceeds by deducing the general case from this one. In the case where X is actually projective, this is the, again, well-known, but perhaps not super well-documented assertion that the Picard stack of X is canonically self-dual. Of course, everybody knows, the Jacobian of the curve is self-dual, and the fact that the Picard stack, which is, just a slight modification of the Jacobian is self-dual, could be deduced from that sort of classical result, but we kind of took a slightly different tack. So first, let me just say, there are two major reduction steps in the proof. So as I just alluded to, the first is to reduce to the case where G is actually the classifying stack of GM. I hope, it's plausible that this is a reasonable thing to do. Clearly, BGM plays a special role, right? Because the condition on the target stack that I put is that it's one reflexive, something about one Cartier duality. So how does this reduction step proceed? So it's a little bit of, there's probably a few different ways to do it. So I think I originally conceived of a different argument, and now we'd like to do it in a different way, but let me just kind of sketch how that goes. So any commutative group stack can be resolved in the following way. It sits in a cofiber sequence as written here. So this notation means that for any affine scheme S, I write Z adjoin S for the free sheaf of abelian groups on S. Okay, and then any commutative group stack can be resolved in this manner. So if you think about commutative group stacks as something like sheaves of complexes of abelian groups concentrated in degrees 0 and -1. Hopefully this looks very reasonable, right? So we can always write down this kind of resolution, and dualizing, we obtain a fiber sequence which realizes G dual is the fiber of this map between these funny looking stacks written here. So essentially, this says that any one reflexive G, it can be built up from commutative group stacks of the form maps from an affine scheme into BGM by taking products and fibers. And if you think about it, because both sides of this Albanese isomorphism sort of commute with products and fibers, this allows us to reduce to the case where G equals BGM. Again, looks like a very funny argument to me, especially the first time I saw it, but then I realized there's some precedent for it. It's a little bit like in classical arguments about Pontryagin duality. People sometimes use the trick where if I have a discrete abelian group, of course, I can write down a two-step resolution by free abelian groups. And then dualizing, this tells me that any compact abelian group can be written as the kernel of a map between possibly infinite dimensional tori. So it's a little bit like this, actually. It's not totally out of the blue. All right, and so having reduced to the case where G equals BGM, the other reduction step is, again, kind of an old idea that goes back at least to, in the geometric setting, to this famous letter from Deligne to Serre, where he explained that this kind of Albanese property, geometric class field theory, might have been what he was thinking about in particular, should follow from, one, the kind of unramified case where X is actually projective, and two, the sort of local version where X is replaced by a formal punctured disk. Okay, so I see that I have about 10 minutes left. So I think what I'll do is I'll very quickly skim over the proof of the unramified case. I, of course, have no time to do anything more, but just sketch it very quickly. And try to say a little bit about the local case. So first, how does this sort of reduction happen? So the idea is like a kind of general global ramified Albanese property has kind of there's sort of a 2 out of 3 relationship between these 3 statements. So the 2 written here, and then the general statement I said, if you know 2 of them, you should be able to deduce the third. And the 2 written here are kind of easier than the ramified global case. So we'd like to kind of deduce the theorem that I stated earlier from these 2 statements. And you do this just as follows. So write L plus GM for the arc group. So the arcs into GM from, meaning like that should be an underlying maps there. So it's the mapping space from the formal completion of the curve at a point into GM. Right? So arc group at every point. And I have a exact triangle which realizes this Jacobian as an extension of the Picard stack of the projective curve X bar by essentially this arc group, or finite limiting copies of this arc group. So somehow the unramified case is something about the Albanese property of the Picard stack of X bar, and the ramified case is something about some kind of Jacobian property of the arc group or the loop group. So that's how we perform this reduction, is by exploiting this exact triangle. Okay, so again, very little time. Maybe let me skip over the unramified case. So what's written here is essentially what's written in my old preprint. So there's nothing really new here. So let me refer you to that, or you can ask me about it later. But I think it's more interesting to kind of focus on this ramified case, which is much less well documented. So in the local case, I'll fix a closed point, small x. The role of the local Jacobian is played by the loop group of GM, which is defined by the formula here. So this is the usual algebraic loop group, loops into GM. And here, so K, capital K sub X, it's the fraction field of the completed local ring, curve at the closed point X. So this is kind of the local Jacobian. So the kind of main fact here, which was written down by Cartier, following some ideas of Grothendieck, is that there's a canonical perfect pairing on this loop group into GM. So in other words, this loop group, it's canonically self Cartier dual, but 0 Cartier dual, right? I'm taking it's a pairing into GM, not into BGM, which makes sense because this loop group, it's kind of in the affine, right? So it's the kind of thing that you expect to sort of work with the zero Cartier dual. And well, again, Cantu-Carrere made this observation. I proved this originally. And you'd like to say that this pairing is induced by some kind of local AutoJacobi map, right? So in an ideal world, you know, if I write, use this notation, D punctured, right, for the spectrum of the local field, then you would sort of hope that there would be a map from the punctured disk to the loop group. And you can even kind of, in a fantasy world, you might be able to write down sort of how what this map does. So there is some kind of geometric intuition for it here. But in fact, the map that you naively expect that doesn't exist, and this is for a reason which occurs in other contexts as well. Namely, it's the same reason that there's no non-constant map from the punctured disk to the formal disk at X, because in algebraic geometry, if I want to work with Laurent series, all I can do is take the spectrum, right? There's no way in algebraic geometry to take account of, well, at least if I'm trying to attach an algebraic geometric object to this Laurent series, it's very hard to do it in a way that takes account of the topology on Laurent series, right? So if I interpret this disk here as the formal disk, then there's really no non-constant map from the punctured disk to the formal disk. In order to write down such a map, you have to replace the formal disk by just the spectrum of power series, right? Forget about the topology. Then, of course, you have an inclusion from power series and the Laurent series, and you can take spectrum, but you can't mix this kind of punctured disk with the formal disk. And so this local AutoJacobi map, you can write it down using a similar trick. So you have to replace the formal component of the loop group by an affine scheme. It's a little bit subtle to do it, you know, carefully in a canonical way, but it certainly can be done, and that's essentially what Cantu-Carrere did in his original paper. So let me just kind of glossing over all of this, we can just say morally this Cantu-Carrere pairing is induced by restricting, taking a homomorphism from the loop group into GM and restricting it to a map from the punctured disk into GM, which again is a point of the loop group. So that's kind of morally how that pairing is defined. All right, and so if we believe in this version of the local AutoJacobi map, if I replace my target, instead of taking the target to be the multiplicative group, I take classifying stack of the multiplicative group, then I get a homomorphism from this HOM from the loop group into BGM into sort of maps from the loop group into BGM. Again, I should impose this extendability condition, which if you think about it, is exactly just the card group of the punctured disk in this sense is exactly just the classifying stack of the loop group of GM. Because if I require that my line bundle on the punctured disk extends to the disk, any such thing is certainly trivial, right? And the automorphisms of a line bundle on the punctured disk are just the loop group of the GM. So I have this homomorphism, and Cantu-Carrere's results, the content of it is that this map is an isomorphism on H of -1. Now, for our version of the Albanese property, we really need this to be an isomorphism of commutative group stacks as written here. So if we think about what that means, to say that it's an isomorphism not just on H-1, but also on H0, since the right-hand side, its H0 is trivial, right? It's the classifying stack of something. That's the content of this assertion is that the H0 of the left-hand side is trivial. So it amounts to a certain X vanishing result. So again, the formal component is kind of easy to deal with here. So the real content of this statement is that any family of multiplicative line bundles on the arc group of GM is trivial locally on the base. And this actually can be proved in the following generality. If I have any commutative affine group scheme, then the sheaf X1 from G into GM vanishes. I find it very hard to believe that nobody ever proved this before. So we have an argument which, well, it's pleasant enough, but I found it very surprising that I couldn't find this anywhere in the literature. So again, I'm very happy if somebody could point me to that. Certainly many special cases of this are known, but I was unable to find reference for this general fact, which is needed here for the case G equals the art group. So again, that implies that H0 of the left-hand side of the map at the top of the page here is trivial, and that is the local version of the Albanese property that we needed. And that is all I have to say.
Great, well, thank you very much. So do we have any questions in the, I don't think we had any more questions in the chat. I don't know if you wanted to address the Cartier hierarchy of dualities.
Yeah, I think, again, it's something that I'd very much like to understand, but certainly there are additional difficulties already when you start talking about B2 of GM. I don't know how to adapt these arguments in a direct way, but I have some ideas. So I think it probably is true that kind of the statement that you formulate in a similar way, that if I take G to be a commutative group stack like valued in two groupoids, which is two dualizable, then the same kind of statement I expect to hold, certainly. But I think there might be significantly harder kind of technical difficulties. So, yeah.
Did anyone else have any questions or comments, perhaps?
Does Sylvian Burkhardt address the lemma that you're talking about, the commutative affine group scheme G? We have vanishing of X1 in his work on this sort of higher Cartier duality.
Who is that?
So I'll probably say the name terribly. Sylvian Burkhardt, I think.
Oh, Burchard, yeah. No,
sorry.
so I think I'm familiar with the paper you're talking about. It's like something commutative group stacks, Cartier duality, right? Yeah, there's some paper about this. No, he lists a bunch of special cases, which led me to believe that he didn't know the general. So he lists several different G for which this expansion holds, and doesn't ever assert that it's true for an arbitrary affine G.
Okay. One other question, actually, which is, do you know, is there a classification of which commutative group stacks are reflexive or one reflexive?
You know, it's an interesting question. So like my feeling is that I don't know if there is such a characterization. In all examples I know, they're always kind of close to being representable in some sense, but you have to, in a very extended sense. So like they tend to be like indart and stacks or something like that. But whether you could formulate some kind of criterion along these lines, I have no idea. But it's an interesting question if you could give some more intuitive characterization of what it means to be dualizable. Yeah. I don't know. And all the examples that counterexamples where it's, so I can give you an example of something that's not one dualizable. If you take the moduli of Cartier divisors on a global curve, not necessarily effective, just arbitrary Cartier divisors, you can make sense of this. It's gigantic. It's very far from being an n-scheme or anything like that. And that to me is kind of a typical example. So a slightly smaller example would be like if you took the moduli of invertible rational functions on the curve, that thing, its Cartier dual is trivial, which I proved in my earlier preprint on this. And so that's a kind of typical example to me. They tend to be pretty monstrous objects geometrically.
Okay, cool. Thank you.
Mm-hmm. Anybody else? Okay.
Okay, well, let's thank Justin again and all the speakers for today. And yeah, the Zoom room remains open, I think, for another half hour or so. And obviously people can spin off into other chat rooms if they wish.
In practice, people have not actually seemed to be terribly interested in hanging around. But if at any point people want to hang around and have a serious conversation, we're happy to let it happen. But I think both days I've been here for maybe 5 more minutes and things have kind of... I
was going to say, I'm going to linger for a little bit and then go make dinner myself.
Exactly. People have to make dinner. We've got stuff to do. But it's a good theory.
Maybe I can ask a question for Justin.
Sure.
Have you thought at all about the higher dimensional case? I mean, for outside of the situation of curves?
No, I haven't. I'm certainly curious about it, but I feel like every time I've ever seen some version of higher Cartier duality in this, or sorry, higher dimensional class field theory, and this might just be my ignorance, it always feels like it's kind of somehow bootstrapped from the one-dimensional case, and I can never see the additional content. But it might just be my ignorance. But no, to answer your question, I haven't thought about it much. Yeah, it certainly seems like at the very least, I think you would need to introduce derived algebraic geometry to get in right, because the Picard stack would be derived, for example.
Right. Yeah.
But it would be interesting to see if there is anything there. Yeah.
Just a comment, maybe. It seems to me that there could be some similar calculations just in spectra, just for commutative groups. So I thought something like this, but I forgot where I thought it. I mean, just for commutative group in spaces, I mean.
Yeah, what do you mean? So like if I starting with a curve?
Well, I'm not sure what I mean. I mean, just if you have two commutative groups in spaces, well, you may ask about Hom between them. So, right? Such kind of calculation was done, I think, for spectra. It's a calculation of extant spectra.
Yeah. It does kind of have that flavor, right? I'm not sure. So Kafai asks, the main result contains more commutative group stacks than the reflexive ones. No, it's only one. It was formulated for one reflexive group stacks, and it certainly fails.
Interesting. I mean, well, your main result contains some Cartier one dual of the arbitrary commutative group stacks, right? So it contains more than just the reflexible ones. Should it contain more than just the reflexible ones? So the hypothesis is that the Albanese property holds for one reflexive groups. Only?
Yeah, certainly fails in general.
I think that is correct, though. I mean, like the Albanese property seems to hold for anything that's like the dual of a commutative group stack, right?
I see what you mean. Right.
Yeah. Like it doesn't hold for every commutative group stack a priori, but you just need
one dual of them. Yeah. Right.
I see what you mean. Yeah. Things of the form G dual. Yeah. You could probably, right. I think the argument shows that it holds for anything like that. Yeah.
Yeah, exactly.
I don't know an example. What's an example that's not reflexive? I don't know.
All right.
Yeah, but yeah, it does. The argument does work in that generality.
I wonder if every commutative dualizable group stack is of that form. Like if every group stack of that form is actually dualizable.
Well, no, I think it's no, right? Because, so things of the form like mapping space from an affine scheme into BGM.
Oh, right, yeah, of course.
I mean, those are very weird things, but
yeah.
I don't know how to prove that it's not one dualizable, but it doesn't. It seems implausible. I don't know.
Yeah, like maps from A1 to BGM.
Yeah, the whole thing. Yeah. All right.
Yeah, by the way,
actually, right at the start, you said, what did you say? You said something about the Picard stack actually just being like the Picard scheme in the case where you were looking at like...
It's for an open curve. Yeah, because it's rigidified, right? because I fix these trivializations over the formal disks.
Yeah.
And that there's no automorphisms there for an open curve.
Okay, cool. Yeah. Yeah. Okay. Yeah. Duh.
Yeah. If nobody else has any questions, I actually do have to go. So. Okay.
All right.
All right. Thanks, everybody.
All right.
Have a good afternoon.
Thank you. Bye-bye.
Okay.
I have a question for Josh D before he goes. Did you see the chat I sent you, Josh?
No, I didn't.
I wanted to download the chat because there were questions during my talk that it'd be nice to, it wouldn't let me cut and paste them. And it wouldn't let me download them. And I thought, you're host, so it's probably going to save a copy on some local folder. And if you could send it to me, there should be a chat.
I'll see what I can do.
Cool.
Yeah, this must be possible.
I mean, I know when I've done other Zooms, I've been able to just, go to the ... and say download.
And this is one of these things where I always feel dumb suggesting a very low-tech solution, but you can always screenshot them.
A screenshot? I will, if Josh doesn't have luck with the download, I will screenshot.
The host should be able to save the chat in a file. If you set it right, you should be able to save all the even public and private chats as well.